Hello, this is Concrete Path, and the lecture is for the second method of the stresses calculations related to the pre-stress concrete that we call as load balancing concept. Load balancing concept. Okay, so we are going to take a pre-stress concrete beam, with bent cable, with a cable that's bent cable. Okay, let's take this beam of length L, simply supported. Okay. Now the cable is like it's a bent cable. So it's a bent cable. Let's say that the bent cable is somewhere placed here. I would say there is some eccentricity from the neutral axis. Let's say the neutral axis is along this dashed line. Let's say this is the neutral axis, and I would say that the P forces acting at the ends at an eccentricity of E1 above the neutral axis, and the what you call as tandem is at some eccentricity E2 at the midspan below the neutral axis. And similarly from this side also, this one is also E1. We would say this one is also E1, and E2 is at the midspan. So this is the what you call as bent cable. So let's say this is the bent cable, and Prestress force is applied P, and there's some theta here. Let's say the theta here is theta. That's also here theta. That's also theta here. Okay. So now we are going to the concept is load balancing concept. Load balancing concept. So we are going to do we apply what you call as we apply balancing load, balancing load, and we are going to say how much balancing load would there be, and we're also going to say this method is saying that you should assume you have to assume that the cable is straight. Cable is straight. At the level of, and the level of that cable should be uh, corresponding to the level of corresponding to the level of the tendon at the ends. So I would say at the ends, your cable is at E1 from neutral axis. At E1 from neutral axis. That means we have to assume the cable straight, uh, corresponding to the eccentricity of the cable at the ends and at the ends. Let's try to get that. If this was your neutral axis, the cable was at the ends at some eccentricity of E1. At some eccentricity of E1 above the neutral axis. And I have to assume that cable is straight from that point itself and remains straight throughout the length. This is the load balancing concept, and it says we have to assume the cable to be straight. And that too corresponding to the ends where the what is the eccentricity at the ends. We have to keep the same eccentricity throughout the length. So I would write assume cable length from end point of cable. Assume cable is straight from endpoints. After that we are going to keep it as a straight line. Okay, so this is our cable now. Now we need to say, is this force now only P, or there is some component of that? Is this only P force, or there is some component of that? Let's try to cut somewhere. Let's try to take a section somewhere here. I would say there's some point at some location of, let's say there's some location of P. At the location of P, there is a point P. I would say there is some force that's compressive in the bar. It's actually this part. We are cutting this part of the bar. I would say there is some force of P inside. That's compressive force of P, and we say that there is some theta, and there's some theta. I would say the resolution of those forces would be this one is equal to P sine theta, and for this one is also P sine theta, and for this one there's some component of horizontal P cos theta, and from this side also we have some component of p cos theta. So I would say here I would say that similarly, if you take one more section at the what you call as midspan, at the midspan, I would say your force of P is somewhat in this fashion, and one more force of P is in this fashion. Okay, compressive forces. That means if I were to resolve that, I would say there's some net P sine 2 theta. Uh, yeah, to balance that, there should be to balance this one. It should be in equilibrium. There should be some balancing 2p sine theta. There should be some balancing 2p sine theta, as per the theta is this one, and there's one more cos theta there. Uh, uh, that there should be some p cos theta here. There should be some p cos theta here also. Okay, this should be the balancing balancing loads. So similarly, if we are going to take that, if we are going to take that concept, and going to convert it, we are going to convert it now in this fashion, that there is some p cos theta here. P cos theta is that perpendicular to the horizontal, that section, perpendicular to the section, and there's one more load p cos 2p sine theta at the midspan, 2p sine theta at the midspan, 2p sine theta at the midspan. So this is our final configuration of this problem. And then after that, if you want to convert, if you want to have the effect of this p cos theta at the neutral axis, I would say this can be converted into this one, and the load is applied at the midspan with a value of p cos theta, and there is some moment also associated with that, and that is sagging moment pe1 cos theta. Okay, pe1 cos theta. That is a sagging moment about the neutral axis. Okay, and similarly from this side, there's some p force, and there's some horizontal, there's some sagging moment of pe cos theta, and there's some what you call as 2p sine theta balancing vertical load. Now one more thing is that if we take one more case, that's what you call as, if you take in this fashion also, there's a beam, we are placing the tendon in a trapezoidal form. We're placing the tendon in a trapezoidal form. So this can be converted into let's say there's some E value here, eccentricity of E from the neutral axis, and at the I would say at the ends the eccentricity is 0. At the ends, in this case, at the ends eccentricity is 0. So I would convert it in this way, that if you have this theta, if this is theta, I would say okay, I would say that there's some horizontal, it can be converted to some force of p cos theta, and that's passing through the neutral axis, and we know that the eccentricity at the end is 0, so final eccentricity is also 0 for the entire length, and we are going to balance, we're going to have a balancing load here and here, that's equals to p sine theta, and for this location also we have some balancing load of p sine theta. Okay, there might be some external loads also. This cable we are providing corresponding to vertical loads. If there was vertical load here, there was one more vertical load here, W1, W2. If the loads were placed, this was your external load, point load. That's why we have provided the cable in the form of BMD. We say that we are going to provide cables. Cable profile is similar to that of a BMD because of external loads. Because of external loads. See, if the BMD gets developed in this fashion, that's some P, and this is some length of, let's say the load was applied W, so I would say this value is equal to W, and this length is L, so this is your bending moment, and corresponding to that, this was your sagging bending moment, and we place the what you call as, we place the cable in such a way that it's similar to that of a BMD of that beam corresponding to external loads. Then we are going to have the cable similar, we are going to have the tendon similar to that, but we're keeping it in such a way that it produces hogging moments, negative moments, such that it can counteract the effects of those external moments also. Okay. So this was your trapezoidal cable. Third one is that if you take that uniformly distributed load, let's take that we were having some uniformly distributed load. I would say the first one, we are keeping this band cable corresponding to that because we are having some load that was external load applied at the midspan. Okay, let's take third one, that we are having some dead load and we are having some live load such that the intensity is W external. Let's call it as W external, UDL. And there's some simply support a beam, and I would say I'm going to place the eccentricity of the cable in this way. I'm going to place the cable in this way, such that eccentricity, there is some eccentricity at the 2 points. There is some eccentricity E1, eccentricity E2. At the midspan, there is some eccentricity E2 below the neutral axis, and at the ends, we have eccentricity of E1 above the neutral axis, and we are having this cable as a parabolic cable. So your tendon is a parabolic. Tendon is parabolic. Why we are keeping this parabolic? Because we want to have the we have to have the cable. We are going to have the cable similar to that of a BMD corresponding to the external loads. Because of the external loads, we are having some BMD in this fashion, WL square by 8 external. Okay, so similar to that, we are going to have the cable in such a way such that those external moments are balanced by this cable due to producing the hogging bending moment. Okay, so to calculate to calculate the net value of this one, to calculate the balancing load for this one, we had to go for the justification. We call that as justification for use of parabolic cable. So I would say it can be converted to some value such that the eccentricity at the end was initially E1. Eccentricity at the end was initially E1, and I had to keep the cable as a straight line throughout the length with some eccentricity of E1. So this one is your what you call as this one is your first part, and I have to say the component along this horizontal is P cos theta. If there is some theta, let's say there is some theta here, so this would be P cos theta. And after that, I'm going to have some balance load, and that's not a point load. That is also a uniformly distributed load. So the balancing load is a UDL. So balancing load, I can call it as WB, and that value is equals to 8PE cos theta by L square, or we can say 8PH cos theta by L square, where your value of H is E1 plus E2. So 8PH cos theta by L square. So we are going to have the proof for this one, H1, how we get this value, 8PH cos theta by L square. Let's try to get that problem here. Let's try that justification of that parabolic profile. Justification for parabolic profile. Justification for parabolic profile. Okay. That's we say this is a load balancing concept of this cable. Okay. Let's assume that we say that this cable in suspension bridge cable, we can assume that this cable that this what you call as this tendon, we can assume that this tendon is similar to that of a cable. This cable is similar to that of a tendon here. If I assume that this is similar to that of a tendon, then I would say if there was a tendon, if there was a cable, and it was simply supported at the ends, and at this two supports are at the same level, and I am applying some load of, let's say this is some load of equivalent load. I would call it as balancing load. I am applying some balancing UDL out, that's external load. Let's say there's some external load on the horizontal span of balancing load, WB. Okay, I would say because there we have supports, here would we be having some horizontal reaction, and we are having some vertical reaction RV, and at this location also we are having some reaction B, and there's some horizontal, and we know that horizontal reaction is same for the cables. So this one would be some resultant. So this one would be some resultant. Let's say this is some P, we call it as resultant, where your P is S square plus RV square, root of that. So there's some force of P here, resultant. I would say if I use the property of that cable, do you know the property of cable? That moment, bending moment in the cable everywhere is zero at each section. At each section, bending moment in the cable is zero. If I take any section at the midspan, at there's some value of sag at the midspan equals to H. There's some sag of midspan equals to H. So I'm going to say bending moments, summation of moments at midspan equals to zero. That means I would calculate that reaction V into L by 2, that's clockwise, and we have that horizontal into some H anti-clockwise, and we have some UDL. We have some UDL anti-clockwise WB, WB, then we have WB, WX square by 2, WX square by 2. So this is your effect of the UDL, and this should be equals to 0 because bending moment at midspan equals to 0. And can you tell me what is the reaction V? Can you tell me what is the value of reaction V? Is this equals to WL by 2? Is this equals to WL by 2? I think it is equals to WL by 2. So finally it comes out to be equals to this one, and we can say your horizontal equation, your value of H, that horizontal tension, we can say that equals to WB L square by 8H. So this is your equation for the horizontal. This is your equation for the horizontal. Now I would say if there was some cable, now if I take that similar case, if I take the same case in a beam, and there is some cable, parabolic cable, and there's some force of P, there's some force of P. Can I resolve this force P? I would say it's having some component of P cos theta here. It's having some component of P cos theta here. Can you say what is this P cos theta? If I equate that, I was saying that for this case, this was some value of H. P cos theta was equals to H. If I take that P cos theta equals to H, if I say this is P cos theta, can I get the value of balancing load, balancing UDL? Can I get the value of balancing UDL? Let's call it as balancing UDL. So balancing UDL would be equals to P, I would write 8P H cos theta by L square. 8P H cos theta by L square. So I would say your balancing load is equals to 8P H cos theta by L square. 8P H cos theta by L square. Then after that, once I got the balancing load, I can say this can be solved in this way, that we are having some net UDL. We are having some net UDL, that is W external minus W balancing, and it depends on the values such that we can have either positive bending BMD final because of the loads, or we can have negative BMD because of the loads, negative BMD. It depends on this value. If the value is positive, if the net is positive, we can have bending moment as positive, BMD positive. If the net value is negative, we can have net value of moment as negative. So diagram would be negative. And the eccentricity part, we can solve that. I would say finally I can have this one. I can have this one. Finally, this can be finally converted. This can be finally converted in this way, that we have this neutral axis, and the load is P applied at the neutral axis, and we have, this is P cos theta. So P cos theta is applied at the neutral axis, and because of the eccentricity is above the neutral axis, so it would cause a sagging bending moment about the neutral axis. So I would say clockwise here, PE1 cos theta, PE1 cos theta, and from this side also we are having some PE1 cos theta, and we had some external loads also, W external. Now I'm going to say this is some net value. Let's say there is some net value of downwards, W external minus W balancing, or we can keep it as W external, and we are also having some W balancing here, W balancing. Then finally I can solve that. I can solve that. I would say there's some P by A because of the direct forces, and there's some plus minus because of the sagging moment of PE1 cos theta by z. And one more is there. That's I would say net value of moment is because is would be equals to WL square by 8, and this is W net. And let's assume that this is positive. So accordingly, we can get WL square by 8 and divided by z. So these are your values. So this is the load balancing concept. Okay. Now we are going to take that. What should be the equation of this parabolic cable? What is the equation for this parabolic cable? Do you know the equation for parabola? Is that 4hx L minus x by L square? So same equation we can derive for this part. We can derive the same equation for this part. We can derive the same equation for this part. Let's take that. This is our cable. This is our cable, and there's some balancing load of WB. There's some balancing load of WB, and we're having some cable in this fashion. We're having some cable in this fashion. Now there would be some resultants of those that tension. Resultant of that tension would be some horizontal H and some vertical RV. And what we are going to do, we would say the eccentricity at the midspan is equals to H. Now we want to say what at particular value of X, there is some value of Y, and I want to calculate the value of Y. What is the equation for that? That means what is the value of Y? What is the location of that cable? What is the location of that cable when I am going from origin to some value of X? At that location, where should I place the cable such that I can have balancing UDL that counteracts the external bending moments because of those external loads. So that's the what we can say justification for the parabolic cable. Why we are going for the parabolic cable? Okay. So I would say the reaction RV would be equals to WBL by 2. Can would the reaction would the reaction be WBL by 2 vertical reaction? Yeah. And let's say that the horizontal is P cos theta. Let's say that the horizontal is equals to P cos theta. And if I solve that, summation of moments at the X section is equals to 0, because this is a cable, and we can say bending moment at X equals to 0. So let's try to calculate that. I would say your horizontal into some value of Y, that's negative about the section X, anti-clockwise, and we have also anti-clockwise because of the UDL WB X square by 2, and we have positive reaction V WB L by 2, and value of X equals to 0. If I substitute that, let's try to have that value in this way, that HY equals to WB by 2 LX minus X square. Now if I substitute the value of WB as 8p H cos theta by L square, as per our calculations that we got, balancing UDL of 8p H cos theta by L square. 8p H cos theta by L square. Okay. 8p H cos theta by L square. Let's go for that. Let's try to substitute here. So I would say your horizontal, I would rate your I know that horizontal value is equals to P cos theta. Your horizontal value is equals to P cos theta, and this is your Y, and your WP can be converted to 8pH cos theta by L square, and we have that 2 also in the denominator. So I can write equation in this fashion. So I would write Y equals to 8 times H cos theta Lx minus X square divided by L square, and divided by 2. So we get 4H cos theta Lx minus X square divided by L square. So if the theta value is very less, if the theta value is equals to less, that means cos theta can be replaced almost equals to 1. We can replace that almost equals to 1, because your theta is almost lesser. Your theta is less, so that means we can say Y equals to 4H Lx minus X square divided by L square. Okay, I would say if I keep the origin at the support, if this is the origin, I would say if you go to the value of x equals to L by 2, at that location your value of h is, your location of your value of y is equals to h. I want to see that. If I say at value of y at x equals to L by 2, let's solve for that. That is 4h L into L by 2 minus L square by 4 divided by L square. Is that equals to 4h, that is L square 4 minus 2 divided by 2 divided by 8 divided by, then finally L square. So this is 4 1s are 4 2s are, and this one goes, L square goes, so y equals to h. So your value of y equals to h at that location. So once I got the equation of y, that means this signifies that corresponding to external load, that means corresponding to external UDL, corresponding to UDL external, because of the loads that are external, my bending moment has developed. Okay, my sagging bending moment has developed. Now to counteract that, I have to place the cable in such a way that I have to place the cable at a particular section at some location from the neutral axis, such that it balances the load of, because of that external load. So for that, I would say at particular location of x, at value of x section, at x section, where should our cable be? Where should our cable be placed? Where should our cable be placed? That is the significance of this equation. Okay, I would say, what is the slope? Can you get the slope for this one? If I differentiate it, that's dy by dx, that's tan theta, that's tan theta. So I can get the equation that 4h L minus 2x divided by L square. This is our equation for that slope equation. Okay, slope equation. And I would say the slope at the midspan would be 0. Can you say that slope at the midspan would be 0? If we substitute that, what is the slope at the midspan? Or we can write theta at the midspan would be 0, because if we substitute the value of L minus 2 times x equals to L by 2, and this is your 0, and theta at the ends would be equals to 4HL, this is your 0 divided by L square, so 4h by L. So this is your theta at the ends, 4h by L. Okay, so now we are going to take some problems. Let's take the problems now. So let's go for the first problem. We want to calculate stresses at the top and stresses at the bottom fibers on a section that is at the midspan, section. Okay, and you have to account the dead load also. Account the dead load also. Dead load also accounted. Okay, now the beam is there, and I'm applying the load, that is concentrated load. I'm applying a concentrated load of 180 kilonewton. This is the external load I am applying, and the cross section of the beam is there 400, and this is 600. Now the cable profile is that it's a bent cable. Cable profile is a bent cable. So eccentricity is 0 at the midspan. Eccentricity is 0 at the ends. Let's say there's some neutral axis. This is neutral axis. Okay, and I would say the cable at the ends is at the neutral axis. Okay, eccentricity is 0 at the ends. Then eccentricity is maximum at the midspan, and that value of E at the midspan is equals to, this part is equals to 140 millimeters. This is 140 millimeters. 140 millimeters. And this is having some force of P. This cable is having some force of P. Okay, we can show that that this cable is going outwards in this fashion. Then after that, we are applying some force of P this way. We're applying some force of P on this cable. So can you solve it? So try to solve it. That first one is that by stress method, and one more method we have, second method, that's load balancing method. Stress method and load balancing concept. So try to get the solution by this one, and we have to calculate at the midspan. If I calculate it by the stress method, let's try to calculate it by stress method. Stress method. So I have to take the section at the midspan. I have to take the section at the midspan. I would say if there was a this was your section at the midspan. At the midspan, can you tell me where is the location of that tendon? If this was neutral axis, can you tell me what is the location of the tendon at the midspan? Is it somewhere here? Is it somewhere here? So I have to show that this tendon is somewhere here. It is below the neutral axis at some eccentricity of E equals to 140 millimeters. So then if I say that there's some P force acting, on this cross section, then I can say your forces would be, your stresses can be developed is equals to, this is your P by A, and one more stress because of this P eccentricity below the neutral axis, so moment gets developed, that is hogging moment. So because of that we have stresses, compressive stresses at the bottom and tensile stresses at the top. And the value is equals to P P PE by Z. And there would be some dead load also, and because of the that point load also we can have some moment. So let's try to calculate the moments and the dead load. I would say there's some point load on the beam, simply support beam at the midspan, and we know that the peak value of the PMD is equals to PL by 4. And similarly, there's some dead load also as a UDL, and we have the peak at the midspan equals to WL square by 8. Let's calculate the dead load. I would say the dead load is equals to gamma times, let's keep the gamma as 24. Sometimes we can keep 25, or we can say 24 or 25 kilonewton per meter cube. And the area of the cross section, this is 0.4 into 0.6 meters square. So you would get some WD, that's almost and because of that, when you solve this part, and you would get a value of 25.92 kilonewton meter. And corresponding to this equation, I would say your 180 kilonewton is there. Length of the beam is equals to 6 meters. Length of the beam is equals to 6 meters divided by 4. So this value is equals to 270 kilonewton meter. So net, what is the total moments we have? Positive moments. So this is also positive, and this part is also positive. So total moments of total M all is equals to 295.92 kilonewton meter. 295.92. So I would say there's some sagging moment of 295.92 kilonewton meter, and we have the section modulus of Z, and such that this is sagging moment, and it causes top compressive, bottom tensile stresses. Okay, let's try to calculate those as per the stress method. We're applying a P force value is equals to 1200 kilonewton. So your value of P force is 1200 kilonewton. Let's calculate the stresses. I would say your stresses at the top. Your stresses at the top would be equals to stresses at the top. I would say F top equals to P by A minus times PE by Z, and plus 295.92 divided by Z. And make sure that the units are correct. Try to keep them in the units of megapascal. So I would say P force is 1200 kilonewton, and divided by area of a cross section, that's 0.4 into 0.6 meters square. Then minus times P into eccentricity E. I would say eccentricity at the midspan is 140 millimeters, so 0.14 meters. And this is your kilonewton, and divided by Z, section modulus, BD square by 6. Okay, so after that we have plus 295.92 divided by section modulus of BD square by 6. BD square by 6. Okay, so your stresses at the top is equals to 10.3 10.33 megapascal. And stresses at the bottom would be equals to P by A minus PE by Z. Yeah, this would be positive. Stresses at the bottom is positive, PE by Z, and because of the moments we have negative, M all by Z. So those values you calculate first. After that, you can have plus minus of that. This changes to minus plus, this changes to minus. So we can have those values. Finally, 0.33 megapascal negative. That's tensile stress. 0.33 megapascal negative. Okay. Now we need to calculate the stresses because of the using the concept of load balancing. Load balancing concept we have to use. So let's have the load balancing concept. Let's have the concept of load balancing. Load balancing concept. Okay. So your band cable can be transformed such that its eccentricity throughout the length, equals to the eccentricity at the ends. Your eccentricity at the end is equals to 0. So that means your eccentricity now in the load balancing profile is also 0. So that means the cable is a straight line along the neutral axis. Cable is a straight line along the neutral axis. So this is your neutral axis, and the cable is along the neutral axis. So this is along the neutral axis, and there's some P force, and we had to resolve that force, and we know that this P component here would be P cos theta. Similarly, from this side, we can say this is P cos theta. And there was some at the point that was at the midspan, we had some balancing load of 2p sine theta. This was your balancing load, 2p sine theta at the midspan. And there was some external load also. External load is also there, 180 kilonewton. And what is the value of P? P value is 1200 kilonewton. Can you tell me what is the value of sine theta? If you have this triangle, this is theta, and we have this 140 millimeters. We have this total length of the beam is 6 meters, so this part is 3 meters. So I would say sine theta is 140 divided by some 3 meters square, or we can write 0.140, 3 square plus 0.140 square. So this is almost equals to tan theta. This is because your theta is small. This sine theta is almost equals to tan theta. So we can write your sine theta can be replaced. So we can replace this part 2p sine theta as equals to 2p tan theta, and it makes the calculation easier. You don't have to take this root. We don't have to take this root. Then I would say your tan theta would be equals to 0.140 divided by 3 meters. So this is your tan theta. So this value you can substitute here, 2p sine theta. So I would say 2p tan theta can be converted to 2p tan theta can be converted to 2. P value is, what's the value of P we have? 1200 kilonewton. 1200 kilonewton. And tan theta can be replaced here, 0.14 divided by 3. And that overall value would be equals to, let's try to solve it, 24 by 3 into 0.14. That's 112 kilonewton. So 112 kilonewton is acting upwards. This is the balancing load, 112 kilonewton. And there's some downward load also, 180 kilonewton. So I can have this finally in a diagram that we have a beam, and some load is acting, horizontal load of P cos theta along the neutral axis, and there's some net value of, there's some P net of 180 and minus 112 downwards. So net value of P net is downwards equals to 180 minus 112. So now we can solve this one. We can solve this one now. I would say there was some dead load also. I think there is some dead load also. Because of the dead load, the moment at the midspan was 25.92. Because of the dead load. There's some dead load also. 25.92 kilonewton. 25.92. 25.92 kilonewton meters. So I would say the final calculations would be corresponding to the load balancing concept. This is your P cos theta divided by A, and there's some eccentricity of that P such that the stress becomes zero, because eccentricity is zero. It's along the neutral axis, so eccentricity is zero at the midspan. We're calculating at the midspan. Okay. And third one is that we have dead load, that is sagging moment of 25.92 kilonewton meter divided by z, section modulus of z. And one more load is there, that's a point load downwards, and because of the downward load, that would cause sagging moment. So I would say there is some sagging moment of m by z. That's 180 minus 112. So this is your point load, and the moment caused by it, that's PL by 4. The moment is PL by 4. So I would write PL is 6. So P into, this is your P net, and length of beam is 6. PL by 4, this is your moment, and section modulus is that BD square by 6. BD square by 6. BD square by 6. So after you calculate those all, this part you already have calculated. I would say cos theta can be converted to almost equals to cos. This is almost equals to 1. We can say cos theta is almost equals to 1, and you can check that also. You can say, you can either take the value of cos theta, or we can ignore it. We can say that either we can keep p cos theta, or we can say this is all only equals to p. Let's still calculate that p cos theta. I would say p is there, and cos theta. What is the value of cos theta from this triangle? Cos theta is base by hypotenuse. This is 3 meters divided by root of 3 square plus 0.14 square. Try to see the value. What is the value of cos theta? This is 3 by root of 3 plus, yeah, that's 3 square plus 0.14 square. So this is almost equals to, so this value is almost equals to 0.9989. So we can say this is almost equals to 1. So that's why we ignore that cos theta part. So we ignore that cos theta part. Still, if you want to calculate that, that's okay. So I would say that your final values of stresses, this we already calculated as P by A. This we have already calculated as P by A from the stress concept. This part we have already calculated. And PE by Z is not there because eccentricity in this case is 0. So this part is over. And after that we have, because of the moments, because of the dead load, we have already calculated in this one. Because of that, we had that moment of 295.92, and in that part we have already calculated a part of that. So that's your one more part. And third one is that you have to calculate the moment caused by this net load, vertical load of 180 minus 112 kilonewton, and that stress would be equals to, this stress cost is equals to 10.33. This is equals to 7. Let's solve it. 180 minus 112 into 6 divided by 4 into 6 divided by 0.4 into 0.6 square. This is 4.250. So 180 minus 112, 180 minus 112 into PL by 4, PL by 4, PL by 4, and BD square by 6. This is 4250. 4250. So this is P, this is L, this is 4, and this is BD square by 6. So everything is okay, but the answer is coming out to be different. answer is coming out to be different value. I would say the value of P by A, the value of P by A, let's have the value of P by A was, the value of P by A was 1200 divided by 1200 by 0.4 divided by 0.6. That's 5 megapascal. This is 5 megapascal. So P by A is 5 megapascal. Okay. And second one is that PE by Z, let's solve PE by Z. PE by Z 1200 into 1.14 divided by 0.4 divided by 0.6 square and into 6 inverse. So that's 7 megapascal. This is 7 megapascal. This is 7 megapascal. And we had to calculate moment MA by Z. Let's calculate MA by Z. Total moment was 295.92 divided by section modulus 0.4, 0.6 square into 6 inverse. That's 12.3. That's 12.33 megapascals. So overall values, you have the sum of all these three, so you can get the value of those. And similarly, calculate the stress because of the this dead load. Let's solve this one. I would say this is equals to 25.92 divided by section modulus Z. So this stress is equals to 10 point. Yeah, this is 1 point, not 10 point. This is 1 point. This is 1.08 megapascal. This is only 1.08 megapascal. 1.08 megapascal. And P cos theta we already know, that was 5. This part was 5. Okay. And third part we have to calculate that value we have to calculate 180 minus 112 into L by 4 into section modulus. Okay, this is 4.25. this value is equals to 4.250 megapascal. So I would say stresses at the top is equals to, your P by A is 5 megapascal. So stresses at the top would be 5 megapascals, 5 megapascal compressor, and this one is also positive, plus 1.08, and this one is also positive, plus 4.250. What is this total value? 4.25 plus 1.08 plus 5. Is this 10.33? Is this 10.33 megapascal? And calculate the FB, stresses at the bottom. That is 5 minus 1.08 negative, and this is also negative. So minus 4.250. So that is equals to this minus this. So that's minus 0.33 megapascals. So this one and this one. Now try to compare the values with the previous case. That's stress concept. What was the values we had in the stress concept? Stresses at the top and stresses at the bottom. This was stress at the bottom, and this is also stress at the bottom. And one more value was there. Stresses at the top was 10.33. We have erased that part. Stresses at the top was 10.33. This was 10.33 overall value, and here we have also 10.33 megapascals. So either way you can have same stresses developed. So either way you can solve. Either you can say load balancing concept, or we can say stress concept. So all those stresses that are same. So let's take that same problem. We are going to take the same problem, but the problem is same problem. We are going to take that, but we have to calculate the stresses at the quarter span for the same problem at the quarter span. That means if the total length is 6 meters, yeah, if the total length is 6 meters, that means we need to calculate at 1.5 meters at this quarter span, L by 4, 6 by 4. At this section of 1.5 meters, we need to calculate the stresses. Okay. Let's go. Okay. This was your problem. Okay. This was your problem. And we need to calculate the stresses at the quarter span. That is somewhere here. At the quarter span, somewhere here. I would say here the eccentricity would be, let's say this eccentricity here would be equals to E at the point P. Let's call it as EP. We need to calculate the eccentricity at that point P. If you want to calculate it by stress method, and after that we can also solve it by load balancing method. Let's solve it by load balancing concept. I think if I try to solve it by load balancing concept, try to solve it by load balancing concept, can you tell me the solution? Because we don't want to erase this stuff we have already calculated. So if I want to solve it by load balancing concept, let's go by load balancing concept. Okay, I would say the cable can be transformed in this way. Okay, there's no change with that. And there is some point load of 180 and there is some balancing load of 2p sine theta, that is 112 kilonewton. Okay, and then there was one more load, that was UDL. So there was one more load, that was UDL, dead load. So this is dead load of 25.92 kilo, 25 point this actually this is not the UDL, this is moment because of the dead load. This is moment because of the dead load, and dead load is actually 5.76. We have calculated that also. 5.76. That was your dead load here. This was your dead load, and we have to calculate the stresses at the quarter span somewhere here. So at this location we need to calculate the stresses. Can you calculate the stresses at this location? So I would say the P cos theta by A is fixed. This part is okay. This part is okay, and this part is also 0. Okay, but we need to calculate the moments at the particular span, at the particular section. We need to calculate what is the moments at this particular section. So we need to calculate the moments at this particular section. So for that we have to see what are the forces that contribute to the moment at that span, at that quarter span. So we need to calculate the stresses at that quarter span. So we need to calculate the stresses at the quarter span, that moment at the quarter span. Let's go for that. I would say there is a beam of 6 meters and we have 2 supports and a load, net load of, let's say the net load was 180 minus 112 kilonewton at the midspan, and there's some dead load of 5.76 kilonewton per meter, and we need to calculate the stresses at this location 1.5 meters. At this location we are having some moment at this location is mx, so we need to calculate that moment. So I would say there's some reaction of 180 minus 112 divided by 2 and plus WL by 2, W into L by 2. So this is your reaction A. So I would say moments at the midspan is equals to reaction A, L by 2, that's clockwise positive, and negative, that UDL of 5.76 into L square by 2. Okay, right, x square by 2. So that's your moments at the midspan. So let's calculate that value. RA value is equals to 180 minus 112 divided by 2 plus 5.76 into 6 by 2. So that's your total reaction. So your total reaction, that's 51.28 into that L by 2, that is 3 minus 5.76 into 1.5 square by 2. So 146. So moments is equals to 147.36 kilonewton meter. Total moments 147.36. Let's see what is the value here. We also had to check there. This is 51.28 into 3 minus 5.76 into 1.5 square by 2. That's 147.36. Yeah. So the moment here is 147.36. That's okay. Let's go for the calculations now as per the load balancing concept. as per the load balancing concept, we have to say what is the stresses we have. So one of the stress is that we say that your beam was there, and external load was there, one P, external load of W was there, and the eccentricity of the cable was in this fashion. So we need to say at this location what was the stresses. I would say this can be converted by the load balancing concept such that eccentricity was 0 for the cable and balancing load was 2p sine theta, and that we calculated as 112 kilonewton, and there was some vertical load and there was some dead load of the beam, and we had to calculate corresponding to those. We said that we have two different stresses. One is your p by a, and one is your, this is your 0 p e by z, this is 0, and third one is that because of the moment we calculated as 147.36, that is sagging moment positive, so bottom tensile, top compressive, so 147.36 divided by z. So we need to calculate the stresses. Let's go for that. I would say stresses at the top would be equals to p by a. Value of p was given to you, and we have already calculated that p by a, that was 5 megapascal, so that's 5 megapascal. So we can say this is 5 megapascal, and we have positive at the top, we have positive value, that is 147.36 divided by section modulus. Beam was having section of bd square by 6, b d square by 6. So that's value is equals to, that is 6.14 megapascal. So overall value, I would say f top is equals to 5 plus this answer, that is 5 plus this 6.14, that is 11.14 megapascal. 11.14 megapascal. Okay. Now we want to calculate it by stress concept. Let's try to calculate it by the stress concept. Stress concept. So stress concept has to say that you had this part, you had this section at the quarter span, and we are having some eccentricity of E equals to 0 at the ends, and it goes to some value of E equals to 140 at the mid, and we need to say what is the eccentricity at the quarter span. At this location, can you tell me what is the eccentricity? What is this eccentricity of EP? So EP would be calculated as per that similar triangles. I would say EP can be solved as, I would say total length was, up to this part, total length was 3 meters, and this length is only 1.5 meters. 1.5 meters. So let's go for that. So E at P would be equals to, if the total value was 140, if the total eccentricity was 140, and I can say that this would be 70 millimeters by the similar triangles. Can I say that this is 70 millimeters? So I would say I had a section at the quarter span such that at that location we are having some eccentricity of that load P, that is equals to EP, and that is 70 millimeters. So that load is applied such that it is causing some stresses of P by A, compressive, direct stresses of P by A, and one more stress is that because of this P into E hogging moment, so we are having top tensile, bottom compressive equals to PEP by Z, and we are also having some load there. We're having some external loads also. One of the load is there equals to 180 kilonewton, and there's some dead load also associated with that. There's some dead load also WD. So we need to calculate the moment at that quarter span. That's at 1.5 meters. We need to calculate that moment. So let's solve that moment here. I would say total length is 6 meters. We are having a UDL and we are having a point load. So we have to calculate moments at this section. So I would say, what is the reaction we have? The reaction is equals to 180 by 2, that is 90, plus, because of the dead load was 5.76, so 5.76 into 6 by 2. This is your reaction, and this is your reaction. I have to multiply it with the length of 1.5. Then I would subtract that UDL of 5.76 into 1.5 square by 2. That's your moment at the midspan. That moment at the quarter span. 90 plus 5.76 into 6 by 2. This is your reaction into 1.5. Okay. Then subtract 5.76, 1.5 square divided by 2. That's a 154.44 kilonewton meter. So because of this moment, there is a sagging moment. So this is positive, negative, positive, negative. So 154.44 divided by Z. So I had to say, what is the stresses at the top? Let's try to solve the stresses at the top now. Because of the stress concept. Stresses at the top. Stresses at the top. So I would say one of the values P by A, and that P by A is also already fixed. That the stress P by A was already given to you. That was 5 megapascals. That is not going to change. 5 megapascals. Okay, this is 5. After that, we have negative value of PE by Z. That PE was given to you as 1200 kilonewton, and E value is equals to 70, 0.070, and divided by Z, PD square by 6. So one more moment is there. One more moment is there. That's M by Z, and that's having a negative value here. That's having a negative value at the, yeah, we're calculating for the top. So it's having a positive value here. Positive value. 154.44 divided by section modulus. BD square by 6. BD square by 6. Okay. So I would say that is 154.44 into 6 divided by 0.6 square divided by 0.4. That's 6.4. That is 6.435. So this part is 6.435. So this part is 6.435. 6.435. And this part we need to calculate. That's 1200 into 0.070 into 6 divided by 0.6 square divided by 0.4. That's 3.5 megapascal. 3.5. So I would say 5 minus 3.5 plus 6.435. That's 7.93. So net value at the top is 7.935 megapascal. 7.935 megapascals. 7.935 megapascals. But what was the stresses? What was the stresses we have? What was the stress? We need to check whether our values are correct. What was the stress at the quarter span by the concept of load balancing? This was the concept of stress concept. This is the stress concept for the calculations of stresses at the top fiber. This was stresses at the top fiber. And what was the value of stresses at the top fiber when I calculated by load balancing concept? That value was 11.14. There's error somewhere. 11.14. So this is 11.14, but we have got this value as 7.935. But I would say this one is correct. This one is correct. So I think there is some error in the first one. The value should be same. The stress should be same. By either way you can say, but the stress should be same. That means there's some correction. There is somewhere correction. We need to check that. We need to check that. Your value of P by A here, that's fixed. Your P by A, that's already fixed. That is 5. So 5 and stress. I have to add some value such that overall value was 7.9350. So it's not 11. It should not be 11.14. It should be final value. Final value should be around 7.9350. We have to see that there might be error in the moment calculations. Because we have moment M by Z. So 147 should not be there. 147. We need to check. So we need to check this calculations. I would say the reaction is 180 minus 112 divided by 2, and plus because of the UDL 5.76 into 6 by 2. This reaction is okay. Reaction is okay. And we need to calculate moments at the midspan. So this is reaction. That's clockwise. L by 2, where your L is. Yeah, this might be the wrong value. Yeah, this is the L by 2, but we are calculating the stresses. We're calculating the moment at the quarter span. So we don't have to write here L by 2. So we have to write here 1.5 actually. That's L by 4. We have to write L by 4, 1.5 meters. And this is your UDL, WX square by 2. That's okay. That means our moment should have been 51.28 into 1.5. 1.5 minus this 5.76 into L square by X square by 2. That's 70.44. So moment is only 70.44. 70.44 kilonewton meter. So this was very huge value. So 70.44 we had to take. 70.44 here. 70.44. This was your moment, 70.44 kilonewton meters, and this part was your section modulus of that meter cube. So you can check that 70.44 divided by section modulus and into 6, that is 2.935. So this part is 2.935. This part is 2.935. So this part is equals to 2.935. So overall values would be equals to 5 plus 2.935. That is 7.935 megapascals at the top. So we had to calculate the stresses at the top by load balancing concept and by the stress concept, and we got the same value, that was 7.935 megapascals at the quarter span section. Hope you enjoyed that problem. Okay, let's go for the third one. Let's take one more. Let's take one more problem. So let's take one more. We need to say what is the stresses at the top. Stresses at the top. Stresses at the top. But at a span, that is mid-span section. Mid-span section and quarter span section. So at these two sections, we have to calculate the stresses at the top. That's FT, 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 and the system is that, and the beam is given to you. The beam is given to you, and it's having some UDL. There's some UDL. There's some live load. We have live load, 15 kilonewton per meter, and we have a cable that's parabolic. We have a parabolic cable. We have a parabolic cable such that eccentricity at the end is equals to 0. Here the eccentricity is 0, but eccentricity at the midspan is some value. So here the eccentricity at the midspan is equals to A equals to 200 millimeters. And if I see the section, if I take the cross section of the beam is that we're having a cross section of the beam in this way. Cross section of the beam is that 700, 400, 700, 400. That means neutral axis is somewhere at 350. So yeah, let's go for that. When you calculate the stresses at the top, at the section that is at the mid span and one more at the quarter span. Is any other data provided to you? The P force is equals to 1500 kilonewton, and the cable is parabolic. So if I try to solve it by both methods, one is your stress concept, second is that a load balancing concept. Let's go one by one. Let's talk about the stress concept. Let's go for the stress concept. First one, that is stress concept. So let's go for that. Firstly, we are going to calculate the stresses at the midspan. Let's talk about the midspan section. So we need to say corresponding to this section, there is some neutral axis. And what is the eccentricity of that cable at the midspan? What is the eccentricity of that cable at the midspan? So that is equals to E, 200 millimeters. So this is your 200 millimeters. So your P force is acting, Prestress force is acting at some eccentricity of E at the midspan such that it will cause stresses of P by A compressive, and hogging moment would cause those negative positive, PE by Z, and one more is there because the moment we have moments at the midspan. Can you calculate the moments at the midspan? So I have to calculate the total UDL. One is your dead load, that's we can say 25 into, let's calculate for 24 kilonewton. Let's take gamma concrete equals to 24 kilonewton per meter cube into section. What are the section dimensions? 400, 700, 47. So your dead load is equals to 7.2. So I would say total UDL is equals to 22.2 kilonewton per meter. And moments at the midspan is equals to WL square by 8. WL square by 8. What is the length we have? Length of the beam is, let's say it's simply supported. Length of the beam is L equals to 8 meters. L equals to 8 meters. WL square by 8. That's equals to 177.6 kilonewton meter. So let's say that 177.6. So we have that one more moment, sagging moment, so it would cause positive negative 177.6 divided by Z. Okay. So we got those stresses. Let's calculate that. We have to only calculate the stresses at the top. So I'm having this value. Stresses at the top is equals to P by A minus PE by Z and plus My by I. That's M by Z. We can write 177.6 kilonewton meter by Z. Section modulus was 0.9, 0.4 into 0.9 square by 6. BD square by 6. Yeah. 700 is there, not 9. So I would say 7. BD square by 6. And we can substitute the values. The value of P was 1500. So I would say 1500 kilonewton by section of that 0.4 into 0.7 square, that millimeter square. Then we have PE by Z. Your section modulus is BD square by 6. So then we have one more, that's moment. This part, moment, M all by Z. So that we have already written there. So the stresses at the top is equals to, finally you can have stresses at the top equals to 1.736 megapascal. 1.736 megapascals. Now let's say that what are the stresses at the quarter span? So stresses at the quarter span means we need to say what is the eccentricity at that quarter span. So quarter span is somewhere here. I would say there's some eccentricity of EP. So we need to calculate this eccentricity at this location of EP. That means your value of X equals to 2 meters. Because your L by 4 is 2 meters, 8 by 4. So 8 meters. So at X equals to 2 meters, we need to say what is this value of EP. If I have this reference, if I have the end support as a reference, and we know that equation for the parabolic case, what was the equation? Y equals to 4hx L minus x by L square, where your value of h was equals to E1 plus E2. But for this case, we have eccentricity at the end is equals to 0. So I would write your h equals to E for this case, that is 200 millimeters. Can we write that? Your h equals to E1 plus E2, but your E1 is equals to 0 for this case. So your E2 is actually equals to 200 millimeters. So let's substitute that. I want to say what is the value of y, and what is the value of y? That means what is the eccentricity of that load P at that section, at that quarter span section, such that I can calculate the stresses. So at x equals to 2 meters, I would say, so y at 2 is equals to 4 h x. Value of x is 2 meters. Total length is 8 meters minus x is 2 meters divided by L square. So you can have a value of y2 is equals to 150 millimeters. So that's also equals to eccentricity EP. We can say that is also equals to EP, because your E1 is 0. Your E1 is 0. That means your value of h is corresponding to the value of E max. That's 200 millimeters. And your value of y at any section is equals to, we have written that as EP. So that's 150 millimeters. So I would say second case of the problem is that we have to calculate at the quarter span. At the quarter span. At that location, I would say eccentricity is 1 EP, that is 150. Eccentricity is 150. Eccentricity is 150. So stresses would be P by A, okay? And this one would be equals to P EP by Z, P EP by Z, and we need to say what is the moment here. We need to also calculate moments at that quarter span section. So this part we had to remove. We had to say what is the moment at the quarter span section. What is the stresses at the quarter span section because of the moment at that quarter span section. Let's calculate that. So I would say what is the stresses at, what is the moment at the quarter span section? Can you calculate that? Can you calculate that? What is this? What is the moment here? So I had to calculate the reaction. So I had to calculate the reaction. I would say there is some support A. So reaction A is equals to 22.2 into L by 2. This is your reaction A. So I would say moment at the quarter span M2, that means at x equals to 2 meters. So moment at 2 is equals to, bending moment at 2 is equals to 22.8, yeah, 22.2 into this 4, this reaction into x. Value of x is 2 meters minus wx square by 2. Wx square by 2. So this is your moment 2, that is coming out to be equals to 133.2 kilonewton meters. 133.2 kilonewton meters. So I had to say this value of m by z is 133.2 kilonewton per meter divided by z, section modulus. So let's calculate those stresses. So we have to just replace that values of one of the values that we have to replace this 0.2 as EP. We have to replace this as an EP value. So this was your 0.150 meters. Eccentricity of EP equals to 150 millimeters. And rest of the things is okay. And we need to convert that moment because of the moment at quarter span. Moment at quarter span. So I would say this was your moment at the quarter span equals to 133.2, and this is moment 2. Okay. So finally, I would say the stresses finally coming out to be equals to, the stresses at the midspan section are coming out to be equals to 2.552 megapascal. So I would say this is F top at the midspan, and this is F top at the quarter span. So we have these two values. So let's take the second concept, that is load balancing concept. Let's solve the stresses by the load balancing concept. Load balancing concept. So can you have a load balancing concept here? If you have a UDL, and we are having a parabolic cable, can you tell me how can you have a balancing loads? What is the value of balancing loads? So we had to write that. So we had to convert that into load balancing profile. I would say this can be converted to a beam having the UDL of that W all. I can say this is W all equals to 22.2 kilonewton per meter, because your W all was 22.2. W all because of live load and dead load, 22.2, and this should be balanced by the what you call as that balancing UDL. So there should be some balancing UDL WB. So your balancing load should be there WB such that is equals to 8p h cos theta by L square. Is that same value, 8p h cos theta by L square? But your value of h is actually E1 plus E2, but your E1 is 0. This part is 0, so your value of h is 200 millimeters. And we say that cos theta is almost equals to 1, so we can ignore the cos theta. Then we generally write that we write that W balancing is equals to 8p E cos theta by 8p E by L square. 8p E by L square, or we can write 8p H by L square. So let's solve that value of WB. Let's solve that value of WB. Is that A times P. Your E value was at the midspan, that was 200 millimeters. Value of E was 200 millimeters at the midspan, 200, okay. 0.2 meters divided by L square. Your total length of the beam was 8 meters. So this is your double balancing. your double balancing is coming to be equals to 37.5 kilonewton per meter. 37.5 kilonewton per meter. 37.5 kilonewton per meter. So I would say because of this one, it's more. It's more. That means upward UDL is more. This is 33. Yeah, this is 37.5. This is 37.5 kilonewton per meter. But the downward load, external downward load, that's only 22.2. So that means there should be net upward UDL. There should be some net upward UDL. And I would say that the cable profile can be converted to a straight line such that the eccentricity is 0 throughout the length. Because at the ends your eccentricity at the ends is 0. So for throughout the length your eccentricity for the cable is 0, and this value is P cos theta. That's also equals to P. We can assume that that's almost equals to P. You can check that also, because your cos theta would be almost equals to 1. Cos theta equals to 1. So we have to solve for this one now. We have to solve for this one now. Can you tell me what's the net UDL we can have? So I would say net UDL is acting upwards. This is W net. That's equals to 37.5 minus 22.2, and it's acting upwards, and it's equals to 37.5 minus 22. 37.5 minus 22.2. That's 15.3 kilonewton per meter acting upwards. So I would say there's some beam. So bending moment. What is the bending moment that gets developed? Is that sagging or is that hogging? I think that's hogging. So this is negative moment, WL square by 8. So this moment at the midspan is negative times. I would say this is negative because it's hogging. I can write it's negative, or we can say this is some value, but I would say that stresses developed would be negative. So moment at the midspan is equals to 15.3 L square by 8. So moment at the midspan is equals to this one, and we can solve that. And can you tell me what is the moment at the quarter span? Moment at the quarter span would be equals to, so here the reaction is 15.3 into L by 2. So this is your reaction. A. So I would say your moments. What is the moment at this point? What is the moment at this location? I would say you have a clockwise moment because of the, you have an anti-clockwise moment because of the UDL, because of the point load. So that point load reaction, because of this support reaction is there. That is 15.3 into L by 2. So 61.2. So I would write 61.2. This part is 61.2 kilonewton, and into this length of 2 meter, and this is anti-clockwise about that section. Okay, then we have plus this UDL is clockwise. Because of this UDL we have clockwise UDL. So that's 15.3 into 2 square by 2, and we assume that there is some moment in the clockwise direction. There is some moment in the anti-clockwise direction. So finally that we can write it in this way. So let's solve that. So minus 91.8 kilonewton meter. Minus 91.8 kilonewton meter. And this one is also, we can say this is negative because we are saying the moment is hogging moment. So moment at the midspan is equals to 15.3 8 square by 8. That's 122.4. This part is equals to 122.4 kilonewton meter. And we have to substitute those values to get the stresses. So let's remove that all other stuff. Let's remove all other stuff. All other stuff we had to remove. I would say this can be now solved. Let's solve first for the midspan. Let's solve. I would say there's some direct compressive load of P by A, compressive stress of P by A, and there's some net, because of the net moment at the midspan, that was some value of 122.4. We are having some value of 122.4, And can you tell me what is the stresses at the top and bottom? Because the net value is upwards, it would create hogging moments. It would create hogging moments. So hogging moment. Because of the hogging moment, you are having stresses at the top as tensile and stresses at the bottom as compressive. Can you say that? So I would write 122.4 divided by z. So we have to calculate stresses at the top. Let's try to calculate stresses at the top. So F top is equals to P by A, that is fixed, it's not going to change, and we have negative value of that 122.4 kilonewton meter divided by section modulus of 0.4, 0.7 square divided by 6 meter cube, and we can solve that also. P by A and this one, that finally is equals to stresses at the top 1.736 megapascal, 1.736 megapascals. And can we calculate the stresses at the top, but for the quarter span? So I would say stresses for the quarter span is also same. Stresses for the quarter span is also same because we're cutting the section here. At that location, your direct force of P is acting there, and one more is there because of the bending moment. Because of the bending moment we have. So for the second part, your moment is going to change. So this part, moment is going to change. All other data is fixed. So 91.8, we have to solve it for 91.8. So your stresses would be equals to finally that value 2.552 megapascals. Now we need to compare these two values with the previous method, stress method. So I would say stresses at the mid span was 1.736. So in this case also stresses at the mid span is 1.736, and stresses at the quarter span was 2.552. Here we have also 2.552. So both equations, both methods are safe. I would say they would give you same values of the stresses. So we can see, is there any other problem? Okay. Let's go for what we call as load balancing profile of cable. Load balancing profile of cable. We call this topic as load balancing profile of cable. Load balancing profile of cable. Load balancing profile of cable. So in this case, we want to completely balance the external load. Completely balance the external load. Balance the external loads. So let's take a first case. That I'm applying the load of W external at the midspan, and I want a cable that's bent cable. And there's some eccentricity at this location equals to E. So I want to say what should be my profile? What should be the profile? That what is the location of E at any section? That eccentricity at any section such that your moment at that section is because of the external loads is completely balanced. So what should be my value? What should be the value of my value of my eccentricity at any location X such that the moments because of the external loads are completely such that the moment at any X because of the external loads is completely balanced. That means that stresses because of the moment is 0. So that means I want that this stresses because of this moment mx by z it is equals to because of that eccentricity of that load P. Let's say there is some P. I want that because of the eccentricity of that P, there is some eccentricity at any location X divided by Z. So I want that this should be balanced by this one. What should be my condition for that? I would say that once I convert it in terms of load balancing concept, I would say it was equals to W, and this part is equals to 2p sine theta. 2p sine theta if this was theta. 2p sine theta. And this was your straight line here. This was your straight tangent, 2p cos theta. Yeah, this was p cos theta. P cos theta. That means your W is equals to 2p sine theta for complete balance. And if I say your sine theta is almost equals to tan theta, and value of tan theta is equals to E by L by 2. Tan theta is equals to E by L by 2. E by L by 2. E by L by 2. So E by L by 2. So I would write 2p E by L by 2. So your value of 4p E by L is equals to W. So that means the what you call as eccentricity at the midspan. Eccentricity at the midspan is equals to W L by 4, and we have this prestress force of P. So this is actually moment at the midspan divided by prestress force of P. So similarly, if I want to say what is the eccentricity at any location of X, I would say moment at that location X divided by P. Moment at the, yeah, we can write it in this way. This is your load of W, and we have the length of X, and we have this what you call as W by 2p. I think it's 2p. Wx by 2p. Is it Wx by 2p? So this part is your moment at the midspan. This part is your moment at the midspan. So if I say what is the moment at the particular section, if I have a particular section, I would say you are applying a load of P. Here the reaction would be P by 2, and the moment here would be equals to P by 2 of X. So P by 2 of X should be balanced by W into not, it is not in this way. It's not in this way. So I would say Wx by 2p, or that's also equals to moment at any x divided by p. So I would say that this is the equation. Or directly you can say what is the eccentricity at that at the critical location, that's at the midspan. This is your equation, WL by 4p. So I would say I am providing you a moment. I had a beam. Let's say how you design this, how you design the cable. I would say I have a cable. I have a beam of length L equals to 10 meters, and I am applying a load of P. I am applying a load of external load at the midspan equals to 200 kilonewton. And you tell me what should be my eccentricity for the load of P equals to 1200 kilonewton. For my Prestress force of 1200 kilonewton, what should be my eccentricity at the midspan? What should be my eccentricity at the midspan? I know that for the vertical load, my profile is corresponding to the BMD caused by that load. So the BMD caused by that load is in this fashion, that triangular. So my profile should be also in that fashion. So I would say what is this value of E at the midspan such that that complete balance of that load is going to happen. So for that I would say your eccentricity is equals to WL by 4P. So that's 200 kilonewton. Length of L is 10 meters. 10 meters divided by 4 into P. Your P value is 1200 kilonewton. And we can say what is the eccentricity at the midspan. 1200 into 10 divided by 4 divided by 1200. So that's if I have this into 1000, so I would get 416 millimeters, 416.66 millimeters. So I should have a section such that it would have some value such that it can have some dimensions. So I can have that after that some eccentricity of E equals to 416.66 millimeters. So I have to ensure that your section is almost equals to is more than that 416 into 2. So your depth should be more than, I would say, 833.33 for this beam. Almost. It should be at least this value. Okay. So second case is that if I take a triangular if I take that load at quarter points, at third points, I'm applying a load of W here. I'm applying one more load of W here at quarter points, at third points of the beam. Let's say this is L by 3, this is L by 3, this is L by 3. So let's generalize that this is X value, this is also X, and this is X. So let's say this is X value, this is X, and this is X. We have simply support beam. and we have to place the cable in such a way such that there is complete balance of that external load of W. So corresponding to these loads, I would say BMD develops in this fashion. Your BMD develops in this fashion. That's having a peak of W into X. W into X. This is your BMD. So similar to that, in the opposite direction, I have to place the cable. That's if I say that eccentricity at the ends is equals to 0, so I would say your cable should be provided in this fashion. Now I need to say what is this value of E? What is the value of E here? So I would say your value of E would be such that once I balance it, if I want to balance it now, I can treat it in this way that we have a two loads acting here, W and W, and I can treat this cable as a straight line with E equals to 0, with E equals to 0, with E equals to 0, and I'm applying those balanced loads of P sine theta at these points. P sine theta, and second one is also P sine theta. P sine theta. So I would say your W should be equals to P sine theta, and that sine theta is equals to tan theta. So I would write that as a tan theta. So I would write what is the value of theta? What is the value of tan theta? What is the value of tan theta? So I would say tan theta is equals to, if I say this is theta, tan theta equals to E by X. So I would say W equals to P E by X. So your value of E is equals to W X by P. So this is your eccentricity at the quarter point. What is the eccentricity at the quarter point? That's your calculation for that. This is your equation for that. And similarly, I want to say what is the eccentricity at any location somewhere here? What is the eccentricity at any location here? What is the eccentricity at there at this location of EX? I would say at that particular location we have some length of X dash. We have some eccentricity of X dash. So I would say what is the eccentricity of that cable at that location? I would say that is EX eccentricity at X dash. EX dash is equals to what is the moment at that location? Let's say this is some load of W, reaction of W, and X dash divided by P. This is your calculation for that. Okay. So main thing is that once you got the critical location, here, I would say it's after that there is a linear variation. So you can calculate that way similar triangles also. Once I got the A critical value, E at the quarter span, E at the third point, so I can say all other data. I can say then all other data. So third case is that if I take a parabolic, I want to design a parabolic that tendon. I want to design a parabolic tendon. I want to say where should be the location? What should be the location of that cable at particular section? At particular section. So for that, I would say I have to balance the UDL. I have to balance the external UDL by that balancing UDL. I have to balance that completely. So for that, let's try the equation. I would say you have this beam. You are applying the external load of WE, and there should be the profile of cable such that I have to say let's say eccentricity is 0 at the ends, and I want to say what is this value of E? What is this value of E at the midspan? So for that, I would say for complete balance of the load, I can equate it in this way that we have this external load of WE, and that can be balanced by this WB. WB equals to 8P H cos theta by L square. And if I say cos theta is almost equals to 1, cos theta equals to 1, and your H value is equals to E1 plus E2 equals to E, because your E1 is equals to 0. So I would write H equals to E. So I would say balancing load is equals to 8PE by L square. So the balancing load is equals to 8PE by L square. So I would say your WE, your W external should be equals to W balancing, that is equals to 8P E by L square. So your load should be such that, now we can say your eccentricity at that midspan should be equals to W external L square by 8P. So this is the equation we have. This is the eccentricity of the cable at the midspan such that your external load is completely balanced by that balanced load. So that's your WE L square by 8P. So external UDL L square by 8P. So we have the value of P fixed. We know that we are providing you a value of P, and we also know that your dead load and live load is such that it's having some load of WE. There's some external load of UDL WE, and we also know the length of the beam as L. So I would say what should be the eccentricity of the cable at the midspan, so that we can solve by WE L square by 8P, such that the stress is caused by the dead load and live load, is balanced completely by the effect of that what you call as balanced load, that is W balanced L square by 8 and divided by section modulus of Z. So that is the meaning here. So such that these two values would give you a 0 value at each point. So stresses for all the fibers is equals to 0. That means the balancing concept is that we want stresses at the all fibers is equals to 0. It's not that does not mean stresses is 0 for the fibers. It means the stresses caused by the moments, external moments, that are balanced by what you call as that are balanced by balancing that are balanced by that balancing load, balancing UDL. So the meaning here is this one. This is the meaning for that. Okay. So one more thing is that let's take a problem for that simpler problem we have. It's given that say L equals to 10 meters. We have a simply support beam. Your pre-stress force is 3000 kilonewton. We need to find the profile. Of load balancing concept by the load balancing concept for this for the UDL of 72 kilonewton per meter. So we have 10 meter beam. Okay, there is a UDL, external UDL 72 kilonewton per meter, and we want to say what is the profile for the complete load balancing profile. Let's go for that. I would say your equation would be such that if the eccentricity at the end is equals to 0, so your cable should be parabolic such that your value at the midspan is equals to E. So your value of E is equals to WL square by 8 is equals to P times E. So WL square by 8 divided by P. So this should be the equation, WL square by 8 divided by P. So W is equals to external 72 kilonewton per meter. L square is your 10 meter, 10 square meter square. 8 times P, 3000 kilonewton. So your value of E would be equals to 300 millimeters. So your value of E should be equals to 300 millimeters. And similarly, if I take one more problem that you had this beam and load 1 W equals to 200 kilonewton and one more load is W equals to 200 kilonewton, and you had this beam of length 9 meters. So this is 3 meters, this is 3 meters, and this is 3 meters simply supported. And I want to say what should be my for complete balancing of that load, for complete balancing of those external loads, what should be the value of E? Get the value of E at the quarter span. That means once I got the value of E, I can say that is straight after that, and then after that a linear variation to the ends. So I would say the profile should be in this way, such that the BMD development would be in this way. So I had to make that cable also in that fashion. So I would say this is the value of E. This is also the value of E. And I know the equation for E equals to W into 3 divided by P. Is that same? Wx by 3. That's we are saying that at this location we are calculating at this location that W equals to P sine theta. W equals to P sine theta, and sine theta is equals to tan theta. Tan theta equals to E by 3. E by 3. So I would say your value of E is equals to W3 by P. And I substitute the values of W. That's 200 kilonewton. 200 kilonewton into value of 3. That is 3 meters. 3 meters divided by P. Divided by P. P value was given to you as Prestress force of P equals to 2500 kilonewton. 2500 kilonewton. So you would get the eccentricity at that third point of the beam, that is equals to 240 millimeters. So that was the end of the load balancing profiles, and we're going to take beautiful two problems now that are a decent kind of problems related to that load balancing concept. Let's take that. It's saying that get the equation. I want the equation of a parabolic cable for the load, for the Prestress force. Prestress force is 1500 kilonewton, and such that external loads are completely balanced. So external load should be completely balanced. Okay. And such that there exists no bending moment at any section. We can also say that the meaning for this complete balancing is that there exists no bending moment at any section. Because of the bending moments, there are those bending stresses. So I want those bending stresses to be zero. So that is the meaning of that load complete balancing. So we are providing you UDL also there. Cable is having some, that beam is having some UDL also. So 22.2. Let's say that some external load of 22.2 kilonewton per meter is there, and it is, I would say this is dead load plus live load. Let's talk about that. I have to get the cable profile. I have to get the equation for the cable profile. Let's say the cable profile is somewhat in this way, corresponding to the BMD. That's some parabolic variation WL square by 8. This is the variation of the cable. I want similar, because I would say the profile would be also similar to that, but I want that equation for that. I want the equation for that. So I would, for the equation, I would say I have to go for particular location of x. At that location, we are having some value of eccentricity equals to y. So I have to write the equation of y as a function of x. That's your equation. Okay. Now I would say from this statement that complete balancing, that means your external loads, those should be balanced by balanced load, balancing UDL. So external UDL should be balanced by a balanced UDL. So I would write equation that for complete balance, you can write for complete balance of that external loads, your external UDL should be equals to balancing UDL. That is, we know that balancing UDL was equals to 8p h cos theta by L square. If I say that h is equals to E1 plus E2 equals to E, because I would say your E, if I keep that E1 equals to 0, so your value of h equals to E. And if I say cos theta is also equals to 1, so I would get the equation as 8p E by L square. 8p E by L square. So I would write that here. So 8p E by L square. That's your, so that external load is balanced by that 8p E by L square. Now because of that, I can get the value of E at the midspan. Because of this equation, I know the value of external load, external UDL. I know that value. I already know that. That was given to you as 22.2 kilonewton meter. So I would say this 22.2 kilonewton per meter is equals to 8p E by L square, and I can get the value of E at midspan. So E at midspan is equals to 22.2 kilonewton per meter into length square. your length of the beam was not given to you. Let's take the length of the beam. Length of the beam equals to 8 meters. We can take the length of the beam 8 meters. So length of the beam is equals to 8 meters. So let's calculate for the L equals to 8 meters. So L square is 8 square meters square, and divided by 8 PE. What is the value of P we have? What is the value of P we have? Yeah, value of P we can take as 1500 kilonewton, 1500 kilonewton, 1500 kilonewton, 1500 kilonewton. So your eccentricity at the midspan is 118.4 millimeters. So eccentricity at the midspan is 118.4 millimeters. So I got the eccentricity at midspan is equals to 118.4. Now I want for all other values of y, for all values of x, I want eccentricity of that cable at that location. So for that I have to get the equation. For that I have to get the equation. And we have also derived one equation for that. We have derived one equation. When I kept that right side as a reference, I kept this as origin. So I would say your equation was y equals to 4hx L minus x divided by L square. That is also equals to 4h Lx minus x square. Lx minus x square divided by L square. So if I substitute the values, I got the limit. I got the limit that if I go to that L by 2, our value of E is equals to 118.4. So if I set that boundary condition that y equals to E at x equals to L by 2. Let's substitute that part here. I would say your value of y equals to E. That means your value of y equals to E at the location of x equals to L by 2. X equals to L by 2. Yeah. So that's we know. That's already we know. So let's have it in this way that what is the value of h now? What is the value of h? Where we have written that value of h is actually E1 plus E2. Okay, value of h is actually E1 plus E2. Do you know that value of h is equals to E1 plus E2? Value of h is equals to E1 plus E2. If I want E1 equals to 0, that means your h is equals to E2. That was calculated as E. That was 118.4 millimeters. So if I set that value here, I would write 4 times 118.4 millimeters, and we have this length of 8 meter length, and we have this x, and we have x square divided by 8 square, that is 64 meters square. So I can have this equation here. I can have the equation, final equation in this way, that this is our equation, and you can simplify it, and I can write that is 7.4 10 to the power minus 3 x times L minus x. We can have a general equation in this way. Okay, let's take one more problem. This is the final, I think. This is the final one. So we had a beam, that's cantilever beam. We have a cantilever beam. So this is cantilever side. This is the cantilever side. So we are applying those. There are some external loads also. There's some neutral axis. There's some neutral axis also. So can you tell me what is the BMD because of that? Can you tell me what is the BMD variation? What is the bending moment diagram we can have? So bending moment diagram is somewhat in this fashion. So BMD is in this fashion. Here theta is 0, here theta is not 0. So I would say this is your BMD, and value of BMD maximum value is WL square by 2, and bending moment at any section. What is the bending moment at any section? Is that WX square by 2? Because your variation is quadratic, parabolic variation. So WX square by 2. If I cut any section somewhere here, I would say the moment here is WX square by 2. Okay. So this is the this is the BMD. Now problem says that, what the problem is saying, we need to find the cable profile, find the cable profile of cantilever beam for this UDL of WE, okay, such that cable profile exactly balances, cable profile exactly balances the external loading. So this means that what should be the cable profile? What that means? That means in this beam there should be some profile of the cable, some sort of cable profile should be such that your profile is balancing the external loadings. That means the moment caused the moments, it means that eccentricity, the conclusion is that, so solution can be started from this statement that, so eccentricity at any x should be such that moments caused because of the external loadings at that section should be equals to the 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 moment because of the eccentricity of that cable, moment caused because of that eccentricity of that cable at that location. So I'm applying that P4 somewhere here. So I'm having some eccentricity at any location. Let's say I'm taking any section at that location. Our eccentricity is some E value. Eccentricity is some value of E or Y, such that I can say your moment can be balanced. Your external moment can be balanced by that P into some value of Y. So such that your profile is exactly balanced. So that's the meaning here. So, but I know one thing. What should be the profile? The profile should be somewhat in this fashion. So profile should be somewhat in this fashion, as per the BMD. I would say if the BMD is in this fashion, so reverse of that would be the possibility of that that cable. Reverse of that is the possibility of that cable. So can you draw that? Profile of the cable? Possible cable profile. What is the possible cable profile? I would say because the moment here is 0, because the moment at the free end is 0, so here the eccentricity should be 0, and because the moment at the end is 0, because the moment at the end is maximum, I had to, and that is hogging, I had to ensure that cable contributes a sagging moment at the ends. I had to ensure that that cable develops sagging moment at the ends. So now I got that. Now I got one thing, that eccentricity at the end is 0, and that cable profile is either is the parabolic variation. Either it can be in this way, or either it can take in this way, parabolic variation. Now you tell me which of these is the best one that we can prefer, that would counteract the bending stresses caused by those external loadings. I would say because of the external loadings, your bending stresses are in this way, that you're having top tensile, bottom compression because of hogging moment. You're applying hogging moment negative. This is because of the external, and I have to balance those. I want stresses to be 0. That means my stress diagrams should be in this fashion. That's some PE by Z. That's bottom should be tensile, top compressive. So such that moment should be, I have to apply the moment in a clockwise manner. So sagging moment should be developed because of the PE. So how should be the profile? If I keep the profile, if I kept the profile below the neutral axis, then I cut the section somewhere here. I would say there is some section and eccentricity below the neutral axis, and it would cause you a hogging moment, and that means it would increase the stresses. It would increase the stresses. Is it? It would increase the stresses. So we're not going to prefer that. So our profile should be such that it would be upwards. That means it's above the neutral axis. Do you get it? What we are saying? So one thing is there. that eccentricity at the end is 0, and my profile should be such that it's going in this fashion. Why? If I cut any section, let me cut any section. Let's cut some section here. I would say there is some section. At that location, I'm keeping the eccentricity of that load P above the neutral axis. This is your value of E that's above the neutral axis. And it would cause that moment, it is going to cause the moment, that's sagging moment about the neutral axis. So it's having the sagging moment about the neutral axis, clockwise. Clockwise, that sagging moment about the neutral axis. You have this section, and it's having some sagging moment about the neutral axis. So your bending stresses are in this way, positive, negative. So that's going to counteract the effects of those external moments, negative, positive, negative, positive, positive, negative. So your final diagram is in this way. So now this is your cable, and I'm applying a P force here. I'm applying a P force here. This is your P force. Now I would say you go to some value. Let's take the origin now. Now this is our origin. I'm keeping the origin as the free end, and I go to some value of x. At that location, we're having some UDL also. At that location of x, I have some eccentricity of the cable as y. So I would say at that section, my cable profile is in this way, such that there is some force of P, and we are having some value of y here, and there's some UDL. There's some UDL caused by, there's some moment caused by that UDL. That's clockwise, and there's some UDL of clockwise W, and this is some length of x. Can you calculate the moments? I would say summation of moments at that section equals to 0. Let's say they have the moments section at that section, I want that to be 0. So I would say your P into y, that should be equals to W into x, Wx squared by 2. So your equation at any location of y would be W by 2 P x square. Now if I set the limit at the location of, what you call as at the location of x equals to L, if I set the limit that if I want to go to the length of, if I want to go to the value of L, if I want to go to the value of x equals to L, and I am going to say there is a maximum eccentricity we can have, equals to E, y max equals to E, then I set this condition. If I say at x equals to L, your value of y is a critical value of E, and we can say that is equals to W L square by 2P. So I can then finally generalize the equation. Generalize the equation. I would say your value of y by E is equals to Wx square by 2P, and this one is your WL square by 2P. So your equation becomes in terms of x as a function that y equals to E times x square by L square. So this is your final equation of that profile. I hope you got those. Thank you for watching this problem related to that load balancing concept of that stress analysis for combined stresses because of the Prestress force and because of that external moments you are applying. Thank you.